All right. So a couple of quick things before we get started here. For those on Zoom who aren't hearing this, and those potentially in class who didn't hear me kind of talking about it, right? The math review and gases quiz, the answers have been updated, but it hasn't regraded it. So I'm just gonna have to manually regrade it, and I'll do that at some point. But I'll get that taken care of. As a reminder, the first homework is due on Friday, okay? Right, for those attending class, you need to turn it in on Friday. For those who are doing things online, I will have an assignment for you to upload your homework to. That assignment is you're going to require a file load. At the moment, I'm not making it a requirement, but I might consider doing it to where I at least highly suggest using the Adobe Scan app on your phone. For those who have to upload files, it is very, very, very simple to use. I got to log into mine. So I'm just going to demonstrate it. But once you open the app, create an account, or whatever, it's very, very easy to scan multiple pages and have it saved as a PDF. It makes my life simpler to have your entire homework as one file and not multiple images and things like that. If ever I want to print something, it being scanned as a PDF makes things a lot easier, because a lot of times we'll make the background white instead of have it slightly grayed or whatever color distortion is there because of when you took the picture, and that saves on ink and other such things. So yeah, I very much encourage using the Adobe Scan app on your phone. It's free. It's very easy to use. Yeah, that's due Friday. If you want, you can also hand your homework in to hand it over to someone else in class, and if they're showing up, you can have them turn it in or whatever. I don't care. But yeah. And I guess that's mainly it on announcements. Yeah. Question 5 on the yeah. Okay. Yeah, I can do that. So right then on Zoom here, right? Do I want you to make it into the PDF file? I very much would prefer that. And again, it's very easy to do that using the Adobe Scan app. Maybe at some point during class, I'll take a minute to log into that and then show you how it works. But yeah, I very much prefer PDFs. It just makes life a lot easier to upload that and me to download it and view it. So, all right. So there's a question that I already list that out. Log back into Canvas. Let's see if it kept me log in. Nope. Great. Right, it was about the Canvas question. Great. Okay. Unit. All right. Let me share this screen as well. Those on that, and I'll remove the blank screen. All right. So it's question number 5 here, right? Right. The question is how is the work done by a virial gas, right, which has a compression factor less than 1, so Z is less than 1 for a virial gas, compared to that of an ideal gas during an isothermal reversible expansion. Okay, assume that the molar volume changes are the same for both gases, right? And then that compression factor is this constant during this entire time. Okay? And so the question is, how does the work of a virial gas compare to that of an ideal gas? Right? Can I compare them, or do I need more information to be able to do it?
So I remember the slide that said since the real gas has a lower volume, so if you went from 0.99 to 4.99 volume, and instead of 1 to 5, so both go up by 4 liters, the real gas, the real gas goes over a greater percentage of change, therefore it does more work than the ideal gas.
Yeah, so in that problem specifically, that was looking at, so let's share this. So from online, or that was on the lecture slides, right? That was looking at a problem where the equation of state was equal to this, if I believe. If I recall, I think equation of state was something like that. Where I had this like excluded volume term. Yeah, correct. Yeah, so I believe this is the equation of state. And so for this, yeah, and so for this problem specifically, right, this kind of excluded volume, it's just going to have kind of repulsive forces, right, or kind of what that's related with, right? This term here is going to increase the pressure of your gas. It's going to decrease the total volume that it can potentially have. Okay. And so that problem on the slides, right, is related with this equation of state, and it it's, you know, the answer is specific to kind of this specific equation of state here, and the fact that we just have this excluded volume term as to why that work real is greater than work ideal. Okay. Right, I think also this was a constant. Was it a constant? No, it wasn't. It was a reversible isothermal expansion as well. But yeah, the work real and ideal was different, and it's because this volume change ended up being slightly different because the effective volume change was different, right? But for this equation online, your equation of state, right? For a virial gas, you could write the equation of state like this, right? Where Z here is your compression factor, right? Where, you know, it's expanded in terms of, say, pressure volume, like 1 plus B prime P plus T prime P squared, so on and so forth, right? You could write that compression factor in terms of an expansion of pressure or an expansion of volume, right? But I can write it sort of like this, right? And we're told in this case Z is less than 1. And it's always less than 1, and it's just a constant over the volume change that we have, okay? So Z here is just a constant we're given in the problem. So the work done by this real gas is just minus nRT times Z times ln V final over V initial, okay? Which, right, for ideal gas, the work is just minus nRT ln V final over V initial. Okay, so we can compare the work for the real and the ideal, right? We see that the only difference here is this multiplication by Z here, which we know Z is less than 1. So that means work real has to be less than work ideal for this gas. And so again, why this is different than the example problem that were on the slides is because the equation of state is different when describing that gas. And so for the first equation of state here, this is essentially in the case where Z would be greater than 1, kind of in the example here, because you just have this excluded volume term. You just kind of have repulsive forces effectively dominating that increases the pressure of your gas at a given volume and such. So, yeah, so that's why those two things differ. Other questions? All right. So back here. All right. So we have n moles. Actually, I think we've already done this one. I'm going to put this on multiple times. Right? We have this equation of state that I just had written out, right? And talked about what is the work done. Okay. Yeah, we did this before. I don't know, right? C here minus nRT ln V2 divided by NB V1 by NB. Yeah. Let's skip it. We've done that. All right. So let's start talking about constant volume calorimetry, work and heat and internal energy changes under constant volume. Okay. And so, right, before we kind of get what is and the final answer here, let's just first talk about right, what is kind of my change, right? If I have some small change in internal energy du, right, some infinitesimal small change in internal energy, what is that related to, right, according to, say, the first law of thermodynamics? What should it be equal to? Yep, right, just dW plus dQ, right? Now, on the slides online, I broke up work into expansion work and other types of work. We're just going to ignore other types of work, basically for the entire class. So whenever we see work, we're essentially just talking about expansion work, right? And so at constant volume, right, what does, I guess first off, I could say at constant volume, what does this simplify down to? Right, what does du become at constant volume? Yeah, just dq, right? Because at constant volume, right, there's no expansion work. Expansion work requires expansion, right? So constant volume, there's no expansion work, right? There it goes. And so, right, change in our internal energy, then the net change in our internal energy just given by the heat, that's been transferred at that constant volume. Right? Okay. So this relationship here, delta U equals QV, is only true for constant volume processes, technically as well for in terms of gases, it would be for ideal gases. But yeah, okay. This is only true for a constant volume process. But something we'll talk about in a minute is true in more general cases, okay? But yeah, so questions about this slide here, right? We got this stuff. Okay. So this leads into, right, online, and the lecture notes online, things like that, talk about calorimeters, right? You've seen calorimetry before in general chemistry and things like that, right? And in those things that have a constant called the heat capacity. That heat capacity is what? How would you define or describe heat capacity? Yeah, right. So, right, the heat capacity is how much energy does it take to, let's say, raise, increase, change the temperature by 1 Kelvin, right? Yeah. Right, what Derek has written there as well, right? So energy required to raise that temperature, change that temperature by 1 Kelvin, okay? Right, that is what the heat capacity is related with, okay? Right, mathematically, that's kind of given by this formula down here, right? CV is the derivative of the internal energy with respect to temperature, right, at constant volume, okay? Right, that change in internal energy, right, is that change in energy, right? How much energy do I need to add? Too much, how much do I need to increase the internal energy to increase the temperature, right? So that change in internal energy over change in temperature, right? It's the same type of thing as what we just described, right, as this heat capacity, okay? And just as kind of a review reminder, right, what are these things kind of related with? If you see CS here, what is that often called? No, remember, specific, right? Right, and that's in grams per Kelvin, or maybe kilograms or whatever, right? But that's, or sorry, no, not grams. Sorry, scratch that. Joules per Kelvin gram. Kelvin gram, right? That up there, right? So specific heat capacity, right? That's given as joules per Kelvin, right? Heat capacity is units of joules per Kelvin, okay? Right? See itself, right? Units joules per Kelvin. A specific heat capacity is just the heat capacity divided by the mass of an object, right? Right, 1 gram or 1 kilogram, depending on what it's given as, right? CM, the molar heat capacity, right? Joules per Kelvin mole, right? But M subscript, right? Molar volume, V subscript M, right? That's the per mole quantity. We'll see this pop up a number of different times, right? We'll talk about molar internal energy change, molar enthalpy change, molar Gibbs free energy change, and other things like that, right? And you'll get these subscript M's, right? And that's just the molar value, which means it's the thing divided by the number of moles, okay? So the quantity per mole, okay? CV, is equal to what? What is that? constant volume heat capacity. So when we talk more about gases, right? So, and I guess CP here, right, is, and right, the constant pressure heat capacity, right? And this is more relevant for gases, right? For solids and liquids, constant volume, constant pressure, heat capacity is just the heat capacity. Okay? There's not really a difference between a liquid or a solid being at constant volume or constant pressure, right? And so CV and CP are mainly used for gases, right? The heat capacity under a constant volume is different from the heat capacity under constant pressure, okay? Right, and the reason is if you have a gas that you're heating under a constant volume, then its temperature changes more rapidly with a given amount of heat added, while under constant pressure, it takes more energy to change the temperature of that gas, because part of that energy goes into expanding the volume of the gas, which is doing some amount of work when that gas's volume expands, right? So CP is greater than CV for a gas, right? And it's because for CP, some of the energy you're putting in to raise the temperature is going towards work. It's going towards expanding the gas, changing its volume, right? Because you're right, heating it under constant pressure conditions, not constant volume conditions, right? And so for gases, CV and CP have a big difference, okay? Right, and then CVM is molar, constant volume heat capacity. CPM would be the molar constant pressure heat capacity, right? Okay. Are there any questions about what is heat capacity? What's it defined as? All right. So the heat transferred in a process at constant volume is equal to transferring heat at constant volume. What's that going to equal? Much work is going to be done if I transfer heat at constant volume? 0, right? No work is done. If no work is done, Q is going to equal what under those constant volume conditions? Delta U, right? And this question wasn't designed to be tricky or anything like that, right? Talked a couple slides ago, right? At constant volume conditions, delta U and Q are equal to each other, right? Constant volume heat transfer is the same as your internal energy change, right? Under those conditions, okay? So D here, right? Heat transferred in the process at constant volume is equal to D delta U. Okay. All right. Just as a reminder, right? We've done kind of math review before, but as a reminder, because we're talking about these partial derivatives, right? Talking about CV is del U del T at constant volume and such. Okay. Right. As a reminder, what would this partial derivative equal here? So here's C, there's the B online here, right? So if I take the derivative of this expression with respect to y, holding x constant, right? That means that, right, 2x cubed is effectively a constant. So I should pull that out, and I'm just looking at d squared dy, which will just give me 2y. So 2y times 2x cubed gives me 4x cubed y. So C here, 4x cubed y. right? Just make sure I kind of verbally said that right. I have 2x cubed y squared del y, holding x constant, right? This is the same thing as just looking at 2x cubed times dy squared dy, which is 2x cubed times 2y, right? Which gave us that 4x cubed y. Okay. Questions? All right. So let's say I know the internal energy for a nonlinear polyatomic ideal gas. U is equal to 3 RT. What is the constant volume heat capacity, CV, of this gas? 1.5 R, 3 R, 6 R, or none of them? On Zoom here, I have some people saying B, right? So, right, to go back, right, the mathematical definition of CV, right, that constant volume heat capacity is du dt, holding everything else constant, right? So if I look at this and I take the derivative of u with respect to temperature, holding everything else constant, I get ddt of 3RT, right? Which just gives me 3 times R. So B here, right, would be the constant volume heat capacity of my gas, okay? Assuming U is equal to 3RT. Right? All right. Right, just kind of go over this slide. So I wanted to just make sure to hit home some of these points, right? C is an extensive property. It typically does change with temperature. How often we will assume it's constant with temperature. So in a problem, unless you're told otherwise, you can assume heat capacity is constant with temperature. If it's not, you will be told like the heat capacity varies with the temperature range in this problem or something like that, right? So you will explicitly be told, hey, the heat capacity isn't constant with temperature, right? Or maybe, yeah. And so otherwise, we'll assume it's constant with temperature over the temperature range of whatever problem we're interested in, right? Things like specific heat capacity, your molar heat capacities, right, are intensive, right? That's just because you can get an intensive quantity by taking 2 extensive quantities, the ratio of 2 extensive quantities, right? Number of moles is extensive, heat capacity itself is extensive. Take the ratio of those 2 things, you get an intensive quantity, okay? Right? And again, we show, or we presented and said, hey, this heat capacity at constant volume is related with the derivative of U with respect to temperature, okay? Right? In this class, we often just, whatever, del, who cares? Let's just write that as D's, right? And so, right, what I did in the slide, and let me just do it more in detail here, right? Del U, del T, constant volume, equal to CV, right? Well, for the sake of this class, right, we're just thinking this is du dt equals CV, okay? Like, who cares about these partial derivatives and everything else? So it's the same thing as far as we're concerned, okay? Multiply dt on both sides, right? Multiply both sides by dt, right? And you get du equals CV dt, okay? And now if we assume CV is a constant, right? So assume a constant CV, right? then when we integrate both these sides, right, the integral of du is just delta u, okay, from some, u initial to u final, right, and then for some t initial to t final, right, the CV is a constant, so that just gets pulled out, and then dt just integrates out to be delta t over that temperature range, okay? And so we get this relationship, right, for delta U. Now, often we'll also see it written as du equals NCVM delta T, right, where we use the molar heat capacity at constant volume, okay, right? CV here is the total, is the heat capacity at constant volume. CVM is the molar heat capacity at constant volume. And often we'll see the molar heat capacity at constant volume, just because that's, just often what's given is a molar heat capacity. Okay? Because, right, right, it'd be very annoying for every problem to give the total heat capacity, because the total heat capacity depends on the total amount of stuff you have, right? So if I want to give the heat capacity for a problem with 3 moles of a gas versus 12 moles of a gas, right, they will have different heat capacities, even if it's the same gas, treated as ideal, and so on and so forth, right? So instead, it's just easier to give the molar heat capacity of the gas, right? And then it doesn't matter how much I have, right? That number will be the same for every problem, okay? And so that's why we'll often see the molar heat capacity version, okay? In which case, you're going to multiply it by the number of moles to get the total internal energy change, right? Questions about how I got this equation, right? Right, you can also kind of get at this equation, right, from one of the first slides you said, right, du is related with dq, right? And under constant volume conditions, dq, right, can just be related to CV dt, okay? And then you just go from there to get this, right? Right, dqv, right? The constant volume heat transfer is related with that constant volume heat capacity and some change in temperature, okay? Right, so you can kind of get at that from either angle, if you will, okay? Right, and that gives us delta U is CV delta T, right? And similarly, at constant volume conditions, right, delta U equals QV, so QV is also equal to CV delta T, right? The constant volume heat transfer is also equal to CV delta T, or NCVM delta T, right? Okay. Questions about this? All right. So let's say I give you a problem, and I say, right, I'm gonna heat a gas at constant pressure, right? How do I calculate delta U? What about Q? Yeah. How do I calculate, what equation do I use to get those things, right? Do I know what I need, right? Right. So the answer to this question could also be, we don't know yet, right? We haven't been given that information. We aren't sure, right? Yeah, that could be an answer. Okay. Any ideas on delta U? We know what equation we should use to calculate that. Or if we need something else, we need to wait until later lectures to get that information. I heard something. Let's say that again. I think I heard someone say something. Yes. That is how we calculate delta U. Why can I get delta U as CV delta T and not say CP delta T, right? For a constant pressure process, right? When I found that this is true under constant volume, right? We derived that first equation, if you will, under constant volume, but now I'm saying, hey, now I'm doing something under constant pressure, and I'm still going to use the same formula, right? Same way to calculate delta U. Why am I saying you can do that? What type of a function is delta U? State function, right? Delta U is a state function. It is path independent, right? State function means it does not depend on the path. So delta U does not care, right? When I calculate it, how I got from some initial to final temperature. Could have done it constant volume, could have done it constant pressure, could have done it adiabatically. Does not matter. Delta U, I can always calculate it using this formula, right? Or using the again, the more common formula you'll see is here, right? Is the CVM, right? But whatever the case, right? CVM, the number of moles, if I want to throw that in there, right? But using that formula, that's how I can calculate delta U, assuming that there's no phase changes or chemical reactions, right? If there's chemical reactions, right, phase changes, then it's potentially something different, okay? But assuming number of moles is constant, right, no matter what I do, that's how I get delta U, right? So the change in internal energy for an isothermal change will be what? Zero, right? Isothermal means constant temperature, right? No temperature change. If there's no temperature change, delta T is equal to 0. Delta U is equal to 0. Okay? Right? And so again, this is the wonderful thing about state function, is how you do the change does not matter. Reversible, irreversible, constant pressure, constant volume, whatever, right? As we go through lots of these different problems over the next few weeks, okay, where we talk about expansions and compressions of gases and things like that, if ever you're asked, calculate delta U, this is what you write down, right? You write down that equation. You say, that's the equation I need to calculate delta U. Again, assuming no changes in number of moles, right? If there's a chemical reaction or something, then it's potentially something different. Okay, and we'll get to that tomorrow, or not tomorrow, but Friday. Okay. Right? Assuming no chemical reaction, right? No phase changes, right? Delta U, that is how I get it. Okay? No matter how the change has been done, that is how I calculate delta U. Okay? Now what about Q? So Q is a path-dependent function, so it does not equal CV delta T for a constant pressure problem, and Q is going to be something completely different that we haven't talked about, right? So we haven't talked about yet what Q would potentially equal for this problem. Okay. Often, and when we get more and more examples, we'll talk about it. But often, to get Q, you often use the first law of thermodynamics, right? This is always true as well. Delta U, you can always calculate it as NCVM delta T, and the first law of thermodynamics always holds as well, right? So I can always get delta U from W plus Q, but often what you'll do is work we know how to calculate, right, under constant volume, constant pressure, reversible, irreversible kind of conditions, right? And so often what one would do is calculate work, calculate delta U, and then you'd get Q from this first law of thermodynamics. Okay? Because Q is path dependent, right? And it depends on how I do things as to what the final value of Q is, and that can be sometimes annoying to actually calculate without, say, using this first law of thermodynamics. Okay? Because yeah, Q does not necessarily equal CP delta T. We'll talk about that on Friday as well. Okay, it can equal CP delta T for Q under constant pressure conditions, but it's not. But there's more stipulations than just it being constant pressure conditions. So, yeah. So questions about this? Yeah.
So CV delta T delta T, but you multiply the other capacities by delta T.
Does that equal? It doesn't necessarily equal delta U. Now again, for a solid and a liquid, CV, CP, like the heat capacity C itself is the same thing. So yeah. So for like a solid or a liquid, yeah, because there's really just like a heat capacity. Those are the same things. But for gases, CV and CP are different, and those would be different from like their specific heat capacity, which you wouldn't really talk about for a gas. You talk about CV or CP for gases, right? Solids and liquids, you'll talk about like specific heat capacities. But so yeah, so for like a solid or a liquid, you would say, yeah, the specific heat capacity times delta T would give you like the internal energy change. But yeah, for gases, it's specifically CV, not CP. Because again, that CP, right, that heat capacity for constant pressure conditions kind of includes this expansion energy and things like that goes into heating your gas under constant pressure and changing its volume. And so, right, the total heat that's being transferred is not related with the total internal energy change and things like that. So yeah, CP does not work for gas. So yeah, specifically CV for delta U. Other questions?
You said that we could technically solve this using CP perfect. Right, you talking about that?
So on Friday we'll talk about it, but yeah, like Q can equal CP delta T under specific conditions. I mean, constant pressure, mechanical equilibrium. There might be one more, I can't remember. And assuming it's a constant, and heat capacity is constant. So like those three conditions, then Q is equal to CP delta T. But the mechanical equilibrium is a very important thing. And a lot of times constant pressure expansions are not at mechanical equilibrium, right? The most common example that at least pops into my head about a constant pressure expansion at mechanical equilibrium is a balloon, right? You heat up or cool a balloon, right, its volume changes, but the pressure inside that balloon and the pressure outside the balloon are the same, and it's always 1 atmosphere, right? Because the size of the balloon is dependent upon like what the external pressure is, right? Because the balloon just blows up more and more and more to keep the pressure inside and outside the same, right? Because it can change, its volume changes readily, right? But yeah, so like heating up a balloon, in that case, heat QP would equal CP delta T, but if the pressure inside your system is changing, right, even though the external pressure is constant, then heat is not equal to CP delta T. Okay. Again, right. So again, things like Q and W are more annoying to calculate because they are path-dependent functions, right? Delta U is not. It's very simple. Always, always, always. No chemical reactions or phase changes, use this guy. All right. Know this equation. Very common. Okay. So delta U is equal to the amount of heat transferred when the volume does not change, no expansion work is done, no extra work is done. Just one of these conditions or multiple of these conditions need to be met. All three or none of these. So delta U to equal Q, right? Okay. The volume does not change. Does that need to be true? Yeah, right. The volume needs to not change, right? And then no expansion work being done. that also needs to be true, but those are kind of saying the same thing, right? If the volume doesn't change, there's no expansion work, right? If there's no expansion work, that means the volume hasn't changed, right? So 1 and 2 both need to be true. They're a little bit redundant, okay? And then no extra work is done. That also needs to be true, okay? Right? If there's no electrical work or things like that, again, types of work that we aren't really going to talk about in this class. And we basically always assume that there's no extra work, okay? And Friday's lecture, when we talk about enthalpy and things like that, we'll assume no extra work as well. We basically always assume no extra work, okay? So all 3 of these things need to be true, G, right? All right, so let's do an actual kind of question with some numbers and such, right? So I got 120 milligrams of naphthalene, okay? And that thing is burned up in a bomb calorimeter, right? As a note, right, a bomb calorimeter is a calorimeter, right, that is a constant volume calorimeter, okay? Right, we'll talk about constant pressure calorimeters at some point, right? But if you see the words bomb calorimeter, that means constant volume calorimeter, right? So everything's done at constant volume conditions in a bomb calorimeter, okay? Right, the temperature rose by 2.05 Kelvin in this calorimeter, right? The molar internal energy of combustion of naphthalene is minus 5,152 kilojoules. And the question is what is the calorimeter constant, i.e. the heat capacity for this calorimeter? right? So just as a kind of a reminder, right, problems, like this that we're presenting and going over in class, problems on the homework, are going to be very consistent with types of problems and questions and wording that you'll see on exams, okay? Right, so I on exams, I do not try to confuse you, right? Don't try to present something that's completely different. Sometimes I might have like an extra part to a question that, is maybe something we haven't thought of as a class together, but is kind of a thought-provoking part of a question or whatever that's a couple extra points or something. But for the most part, right, exam questions are going to be designed like questions that we see here and such to work over and do, right? And so we need to feel comfortable doing these questions, going over these questions, right? And if you do, then you should feel comfortable when taking the exam. Okay? So that's just my little spiel to say, hey, use this time that I give you to work on the problem by yourself, to attempt the problem yourself, see how you feel about setting it up and things like that. Okay. And so, right, so in this problem, we're burning 120 milligrams of naphthalene, okay? That changes the temperature by 3.85 Kelvin. I know the molar internal energy of combustion is minus 5.152 kilojoules per mole, okay? Now, I forgot the per mole thing when I originally had the problem up here, so I added that quickly, right? Right, a molar change, right, standard molar internal energy, right, that means per mole, right? If the name of something says the molar value of something, that is the per mole value of that thing, okay? Now, I hopefully, don't make this mistake on homework questions and exam questions, right? And I try to triple and double check things so I don't make a common mistake like that, right? But the units of this should be kilojoules per mole, right? Because it is a molar value, right? Right. Well, your molar mass is, right, grams per mole, right? It is the mass per mole quantity, right? Molar, whatever, is always the per mole quantity. All right. So the question is, what is C, right, for this problem? So let's, right. So I wrote down the things that are given, right? And we know this is a constant volume process, right? So this is the bits of information that are kind of given in the problem. The molecular weight or molar mass isn't given in the problem, but it's just 128 grams per mole, assuming I calculate that correctly. And so, right, and so given the fact that it's a constant volume process, right, that means the heat that my calorimeter, right, so for a calorimeter, right, there's the heat of the surroundings, and there's the heat of the system, right? The system is my chemical reaction, right? And the relationship between these two things is given, they're equal but opposite sign, right? For a calorimeter, right, in a calorimeter, right, the heat given off by the system is absorbed by the surroundings, okay? Right, and so they have the same magnitude. It's just one is absorbing that energy, one's giving off that energy, so they will have opposite signs. Right, the Q surroundings is equal to minus Q system, or Q system minus Q surroundings, right? Where you put the minus signs doesn't really matter, right? And so the question, right? And so Q surroundings, right? Well, that's just my calorimeter constant times the change in temperature that occurred, right? Because the calorimeter works by the system is my chemical reaction that goes off, that generates a bunch of heat. That heat is absorbed by water that surrounds this chemical reaction, if you will, right? Now, not necessarily in the same container, right? But right, like a bond calorimeter, right, will have some reaction container, right? This is where my system's at, right? Where my reaction takes place, and then there's a water bath around that system, right, with some thermometer stuck in, right, to measure the temperature of that water, right? And so the surrounding, right, heat that's absorbed, right, or given off, right, is related with the heat capacity of that calorimeter times the change in temperature of that heat bath of the water in this example, right? Now for our system, right, I have a chemical reaction that's occurring, right? So that chemical reaction, okay, now since it's a constant volume process, the heat given off by that chemical reaction is given by the internal energy change of the chemical reaction, right? And so I know in this case, it's this, right, this is like the delta U for the combustion reaction, right? So that change in internal energy for that chemical reaction, right? So the minus sign sticking around from above, right? The molar value of that times the number of moles gives us the total heat that's given off by that chemical reaction, right? Again, in the problem, we're given the per mole quantity of heat that's given off by combusting, right? By burning up this naphthalene molecule, okay? And so, right, I'm solving for C. Delta T we're given as 3.05 Kelvin, right? Delta U is minus 5152 kilojoules per mole. Okay. Oh, there's an extra minus sign. Sorry, right? So delta U itself is a negative value, and then there's the minus sign that sticks around, right? Here that I'm carrying through. Okay. And then the number of moles, right, is going to be given by the mass divided by the molecular weight. So 0.12 grams divided by 128 grams per mole. Okay. And so, right, multiplying all this stuff out, right, what you can do, right, solve for C is just divide 3.05 over, right? So the final value of C is going to be 5152 times 0.12 divided by 3.05 times 128. That's going to give us a value of kilojoules per Kelvin. Okay. And that, oh, sorry. Right. And that, I'm just going to go back to the slides to show what that number comes out to be. That number comes out to be 1.58 kilojoules per Kelvin. So I'll pull up my handwritten stuff here since I write that number down. Okay. Just so we can, again, review kind of the work here, right? But assuming I plugged in everything right, then that's what it should be. No. So as long as you have the right number with the right units, I'm not going to care that much about what it is. Now, sometimes in a problem, I'll say, like, give the answer in this unit. So I prefer for you to give it in that unit. But even if you don't, I'm not going to take off a point. As long as you, right, like if you put 1.58 joules per Kelvin, then I'll take off a point because that's not the right unit for that number, right? Like that's just not the right answer, right? Right, which again is a common thing done with work. When calculating work under constant pressure conditions, right, often people will put, right, pressure times volume and then write down that number as joules, which it's not joules, it's liters, atmospheres, right? And so it's, while you did the math right, you did the equation right, you still, right, did the very last step wrong of right, writing the correct units or making sure it's written in joules and converting from liters to atmospheres to joules, okay? And so, you know, that will be a point taken off on an exam or things like that, right? But that's it. It would just be like a point, but yeah. So, but if you convert this to joules and put, you know, 1,580 joules per Kelvin, that is fine by me. Okay. Yeah. So yeah, and Tyson here is asking. I thought it was joules per Kelvin. Right, so you could give heat capacity as, right, I mean, kilojoules is just joules times 1,000, right? So then again, this would be 1,580 joules per Kelvin, okay? Right, right, it's the same thing, like the internal energy up there is written as kilojoules per mole. I could write it as joules per mole by multiplying it by 1,000, right? I could do like megajoules per mole or something like that, right? Right. It's like the mass itself and the problem was given in milligrams. I wrote it here in grams, right? Because I converted milligrams to grams, right? But it's the exact same number as long as I have like the milli, right? It's in the same base unit of grams, right? Milli, kilo, pico, nano, whatever, right? Well, kilo here, right? That K is just implying it's times 1,000, right? Right. So kilojoules is 1,000 joules, right? And so that's right. I just wrote that out for no one to see but myself. Right. But yeah. So again, having the final answer, like if it asks in joules per Kelvin, then for sure, try to remember to write it out in joules per Kelvin. But if you stopped here and the problem said write the answer in joules per Kelvin, I'm not going to take off a point for that. Because I would often do that myself, and I don't care that much. But do at least keep in mind what the problem says in terms of the units at once. Okay? Because often problems might have multiple parts, and the units I ask for in the first part are probably the units that are best to use for, say, the second part and things like that, right? So often, it is better to try to use the units that are asked in a problem, assuming they're asked for a specific time. So, questions about this example here? Right, so we're going to do another example, another calorimeter problem. Now here in this problem, I take 0.5 grams of wire I use to ignite 3 moles of C3H8 and a constant volume calorimeter. The temperature increases by 3.2 Kelvin in this calorimeter. I know that when I burn this wire, I get for every gram that's burnt, I get 400 joules of energy. And I know the heat capacity of my calorimeter is 500 joules per Kelvin. And so the question is what is the molar internal energy of combustion for the combustion of C3H8? All right, so I'm going to have us start kind of talking about this together here. All right. So, again, I'm writing down just the bits of information given in the problem, right? All might be relevant, some only might be relevant, but it's good to just write it down. And we know this is at constant volume, right? So we know this calorimeters, right, burning this stuff at constant volume, okay? And I have the mass of my wire and other things like that are given, temperature changes and such. The question is what is the molar internal energy change of combustion of my C3H8? Okay. So, right, if I want to kind of work backwards to like figure out what I need and how I need it and so on, right, I can think, okay, how would I calculate delta UM? Well, I know, right, that Q for my reaction, right, that heat that's released by the reaction is equal to the change in internal energy of that reaction, right? But I don't know what the heat was given off by the reaction, okay? But I do know the amount of heat, right? I do know the Q for my surroundings, right, is related with C delta T, okay? Right, and I know what C is, and I know what delta T is, so I can get the heat in my surroundings, okay? And so the question is what is the relationship between the heat given off by the reaction and the heat absorbed by the surroundings? Right, they're opposite. I don't know if Derek, you wrote that recently, if that was from a while ago, but if so, right, they're opposite in sign. So there will be a minus Q, say, for the reaction, okay? But in this problem, that's not quite it, right? Because what I can write is, in general, let me write it like this. I'm going to put, right, this is minus Q of the system, right? Q of the surroundings is minus Q of the system. That's true, right? That's always true for these calorimeter problems, right? Q system is minus Q surroundings, or Q surroundings is minus Q system, right? But the question is what is the heat transferred from my system? Where is heat being released from my system? Right, from the wire, right, wire and my reaction, right? Right, in this combustion chamber, I burn some wire to ignite this reaction. That wire gives off heat as it burns, and then my reaction gives off heat as it burns, right? So the total heat given off by the system is just the sum of those two heats, right? And so Q surrounding, right, is C delta T, right? Then minus the heat for the wire, right? It's like the specific heat of the wire or something like that given up, right? Is that 400 joules per gram, and I burned off 0.5 grams, okay? So that's the heat given off by the wire, okay? Right, the wire is giving off that heat, okay? So it should have a negative sign there. Right, yeah. And then here, right, I have the heat from a reaction, okay, which is related with delta U for the reaction, right? Right, my change in internal energy for my reaction, right, is related with the heat given off by the reaction. Okay. Right. So plugging in for these things, right, 500 times 3.2, okay? And that's equal to minus, right, this is usually going to be negative 200, right? 400 times 0.5 is 200, so, right, and then plus Q reaction, right? So multiply 500 by 2.2. What's that? 1600. Okay. 100, right? And then that's going to be plus 200, right? Because there's a negative and that negative. Oh, and then subtract it over. Sorry. Yep. Thank you. Minus 200, right? So this right side simplifies to 200 minus Q reaction, right? So 1600 minus 200 equals minus Q, the reaction, right? So that's 1400, and put the minus sign on the other side, right? So the heat transferred from my reaction is minus 1400, which is that internal energy change of that reaction that occurred, right? but that internal energy change was for burning 3 moles of my reactants, right? And so, right, and that's joules, right? And so if I want the molar energy change, that's just delta U divided by the number of moles, right? Which is minus 1400 divided by 3. Okay. That doesn't evenly go in. Okay, yeah. Minus 466 or 67, or whatever, right, 0.7. Right, joules per mole, right? And so that is the molar internal energy change for this reaction, right? Okay. So questions about this? Right, for this problem, right, like a lot of the problems, right, the key steps are kind of setting up some of these initial equations, and then it's just kind of doing some algebra, right, rearranging some variables, plugging into a calculator, right? And the key steps here, right, is this first relationship, right, Q surroundings is minus Q system, right? And then identifying that the Q of the system is Q wire plus Q of the reaction, okay? And then from there, right, we just plug in for what the heat transfer was from the wire and the heat transferred from the reaction. Okay? And then eventually simplified. So questions about how we did this problem? Okay. Right. It's also a slide. Okay. Right. You get this final minus 467 joules per mole. Okay. All right. So I believe, yeah, so that is it for today. Next time on Friday, we will talk about enthalpy, right? And again, on Friday, the homework is due. If you have not started the homework, I suggest that you do so. Okay. Right, the homework for this class is not, it's lots of problems like this and such. These problems, right, doing like 10 or 12 of these problems doesn't necessarily take just an hour or something like that, right? So make sure to devote time to doing the homework. Again, you can work together on it. That's fine by me. Right. Oh, right, and for those, let me real quick, for those who are interested, right, I'll just show this kind of Adobe Scan app here real quick. Let me screen share. Right, so when you open up the app, right, you'll get, retake, right? So I open up the app and it shows kind of these bars. Oh, yeah, I can't, it's kind of funky trying to do it while showing you, right? But you see these little dots and it's capturing it, right? Hold it steady, and you can crop, the picture if you need to, and then you can continue, right? And it adds that document. And then you can start loading, I can do then another page, right? And crop, and it'll take the picture, right? Crop it however I want to, right? Continue, right? And now I have that document. And then once you're done, you can click on the bottom right. Sorry, I probably didn't show that, but click on the bottom right. You see your multiple files, right? My lovely cropping made it all sorts of funky, right? Doesn't matter, right? But you can rotate these things. You can do, whatever editing you want. Don't need to worry about that if you don't want to. And then you just save PDF. And then saving as a PDF. And then you can, once you've saved it as a PDF, you can email it to yourself, right? You can share it, share a copy, save a copy, do whatever things, right? If you have the app open in Acrobat app or whatever, but I can share it. I can then email it to myself, right? If I want to, or things like that, right? So yeah, so the app works well with doing that type of stuff, makes it easier, you can print it, other things. So, you know, just keep in mind, it's relatively simple and easy to use. Okay? Question here, we can attach the notebook paper to the printout. Or do you want us to type up the answers? You do not need to type up your answers. Your handwritten answers are fine by me. You don't have to submit the questions with the answers as well, as long as you label the questions. Please circle the answers and things like that. I don't want to have to go hunting through all of your work to figure out where your answers are and stuff. So please try to at least circle your answers, highlight them in some way. And in terms of office hours, I don't have regular office hours, but I am available to meet anytime. I'm basically free. So if you want to ask me questions, just shoot me an email, right? And I'm happy to set up a time to Zoom and talk with you or with a group of people if you're working on the problems with people, right? That's fine by me. Yeah. All right. So yeah. So other people have questions, I don't have to answer them. Otherwise, you're welcome to head out. Yep.
I was wondering if you could explain what it means by the standard molar internal energy of like the for the naphthalene one.
Mm-hmm.
Like, does that mean that like when it's combusted, is that the energy that it releases, or is that the?
Yeah. So I mean, it's sort of like the enthalpy change of the standard enthalpy change of a chemical reaction. Instead of talking about the enthalpy change here, we're talking about the internal energy change, right? Often in chemistry, we talk about the enthalpy changes of reactions because, as we'll discuss later, right, enthalpy is related with heat transfer under constant pressure conditions, and often in the lab, we're working under constant pressure conditions, not constant volume conditions, right? Often we have beakers open up to the atmosphere and things like that, and things are under constant pressure conditions, right, mechanical equilibrium and so on, so that the heat transfer from our chemical reaction is the exact same thing as the enthalpy released, right, or the enthalpy change in your chemical reaction. But under constant volume conditions, that heat transfer is the exact same as the internal energy change. So, yeah, so the standard molar internal energy change, right? Right. So the standard molar internal energy change of combustion in naphthalene is, right, what is the internal energy change when I burn up naphthalene, which is a chemical reaction, right? C10H8 plus O2 goes to however many CO2s and waters,
And
right?
That's the energy that's released.
Yeah, for that chemical reaction per mole. Mm-hmm.
Okay.
Yeah,
That
it's sort of like the enthalpy released, right? Just now we're talking about internal energy instead of enthalpy, because again, we're working under constant volume conditions, and so internal energy is the more relevant change and not enthalpy.
Does it consider, like, is that just considering the energy that's also required to break the bonds, or is it just the energy that's released when the bonds break?
So the energy the net energy that's released when the bonds break, right? When you go from reactants to products, right? Right. I mean, that's why technically the other problem, right? I had to burn this wire, right? Because technically for a lot of these combustion reactions, right, we have to first supply energy to then have it burn and give off a bunch of energy, right?
Mm-hmm.
That's to get to a certain temperature before that reaction can take place, right? And so yeah, that's just viewing, like, you know, right? That's, if we think about, right, our reaction diagrams, right? There's like something like this, right?
Yeah.
Talking about, right? It's just looking at what is this, you know, change in internal energy from here to here, right? Doesn't care about what is kind of the activation energy, right? The activation barrier and such.
Okay.
Yeah. And in this class in thermodynamics, what we'll talk about, all we care about is here and here, right? Kinetics cares about this part. And we'll talk about kinetics in 3340, but in 3330, we never care about this part. We don't care about barriers and how much energy you got to break the bonds first before forming new bonds and blah, 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 blah. It's just, what are the energy of the reactants, what are the energy of the products, and things like that.
Okay. And my other question was for the PChem lab that is like when you have to take PChem 2,
Yep.
does it include a thermodynamics section or is it all just the PChem 2?
No, there's thermodynamic stuff in there. There's some kinetics. There's some things from this class, the topics from this class as well as topics from next class
Okay.
that are part of the lab. Yeah.
Okay.
So no, a combination of the two classes.
Yeah, I feel like I can do a lot of the problems that are asked. Some of it is just a conceptual understanding that I feel like I'm lacking without being able to like actually do an experiment or see how things change like in person. So
Yeah.
I just didn't know if we were going to go back and be able to work on that again in the lab. So
Yeah, there will be some things. I'm trying to remember all the labs. I can't, off the top of my head, I can't remember all of them, but like there are things related with stuff we talked about in this class in those labs. I know there's at least 2, potentially more. There's only a limited number of labs that are in the PChem lab. So,
yeah.
But yeah, there are some from this semester. So, but yeah, I mean, if you have questions about kind of conceptual things like this, right? What does molar internal energy mean? What's that referring to? Like, I'm more than answer them. You're welcome to ask them, before, during or after class or whenever you want. That's fine. But yeah, I'm always happy to try to help with clarifying things as well.
Okay. Well, yeah, I'll definitely take note of that and try and formulate my questions a bit more so I can ask better questions.
No, it's more than fine, right? I mean, just get the question out there, and a lot of times, we can work through it and figure out what we're really trying to ask and understand. I mean, everyone has that problem, right, with trying to make sure you articulate what you're trying to say properly, and sometimes it's more difficult than others. So
Yeah, I understand that. Well, thank you for your time.
Yep.
You have a good day.
You too.